We end tonight with the clearest pictures yet of Neptune, the most distant planet in our solar system. Take a look. The striking infrared images were taken this summer by the James Webb Space Telescope, humanity's most sophisticated eye in space. In this scenario, it recently detected a staggering cosmic event that has sent ripples of excitement and curiosity through the scientific community. Far beyond the familiar glow of Earth's moon and the orbits of Mars and Jupiter, at the cold edges of the solar system, something colossal slammed into Neptune. For the first time in recorded history, a space observatory has captured the unmistakable aftermath of a massive collision on the surface of one of our solar system's outermost giants. The implications of this discovery stretch far beyond Neptune itself, forcing a re-examination of the dynamic and sometimes violent nature of planetary systems. Before we start, please consider liking and subscribing for more updates. The detection began with an anomaly. The James Webb Space Telescope was conducting a scheduled observation of Neptune's atmospheric activity, part of a long-term mission to study the ice giant's seasonal changes. At first, the data seemed confusing. Bright spots appeared unexpectedly along the planet's surface, bright chaotic patterns of thermal and visual disruption, where normally there would be the smooth, swirling bands of its methane-rich atmosphere. In this scenario, Webb's infrared instruments revealed abrupt spikes in heat signatures concentrated around a specific region of Neptune's atmosphere. These were not minor fluctuations. The scales involved were enormous, suggesting an energy release that could only be explained by a monumental impact. Drawing from the immense detail Webb can provide, researchers quickly pieced together what had occurred. A massive celestial object, possibly a rogue asteroid or even a minor dwarf planet that had strayed from its orbit, collided head-on with Neptune. Estimates based on the infrared analysis suggested that the impacting body could have been tens of kilometers across, traveling at velocities that defy everyday comprehension. At such speeds, the energy of the collision would rival the combined arsenal of the world's most powerful nuclear weapons millions of times over. The force unleashed by this encounter was enough to pierce Neptune's upper atmosphere, momentarily disrupting the planet's deep-layered weather systems and sending shock waves across its ethereal blue clouds. This was not just a simple event of debris meeting atmosphere. It was an astronomical ballet of cause and effect that reached into the very identity of Neptune's existence. The turbulence visible after the impact revealed not only the layers of Neptune's atmosphere in unprecedented detail, but also hinted at the presence of deeper hidden processes at work within the planet's interior. Scientists marveled at the sudden upwelling of material from lower atmospheric layers, thrust into visibility by the violent disruption. This rare glimpse beneath Neptune's typically inscrutable exterior offered an invaluable opportunity to study its chemical makeup, which until now had remained largely speculative. Beyond the awe of the collision itself, the event raised significant questions about the stability of the outer solar system. It had long been assumed that the regions around Neptune and Uranus were relatively quiet, disturbed only by slow, gradual changes over millions of years. The detection of such a massive impact suggests otherwise, that even in the cold, distant reaches of the Sun's gravitational influence, dynamic and cataclysmic events still unfold. In this scenario, Webb's discovery implies that the Kuiper Belt, the massive ring of icy bodies beyond Neptune, may be far more active and chaotic than previously thought. The notion that large objects could be dislodged from the belt and hurled inward at high speeds opens a Pandora's box of possibilities regarding planetary defense and the ongoing evolution of the solar system. The sheer size of the object that collided with Neptune hints at forces at play far beyond the planet itself, perhaps gravitational interactions with unknown massive bodies lurking at the edges of the solar system. The theorized Planet 9, or even rogue stars passing nearby, could occasionally disturb the delicate balance, sending massive objects hurtling inward. If such disturbances are more common than previously suspected, it means that all planets, including Earth, are periodically exposed to catastrophic impacts from deep space, though at vastly differing timescales. Neptune's magnetic field, already one of the most unusual in the solar system, due to its extreme tilt and offset center, may have also been affected. In this scenario, early readings post-collision indicated temporary disruptions in the planet's magnetic environment. This offers another line of inquiry for scientists eager to understand how external forces can shape planetary magnetospheres, a subject of critical importance for understanding planetary habitability in exoplanetary systems. Moreover, the collision on Neptune presents a new opportunity to rethink the long-term geological and atmospheric evolution of ice giants. If impacts of this magnitude occur even once every few million years, they could be a major driver of atmospheric chemistry, internal heat distribution, and even rotational dynamics. Perhaps features observed on Uranus and Neptune, previously attributed to slow internal processes, are in part the scars of ancient collisions that, like this one, dramatically reshaped their histories. In this hypothetical scenario, James Webb's ability to detect the collision and observe its immediate aftermath with such clarity marks a historic leap in humanity's ability to monitor and understand the solar system. Previous telescopes would likely have missed such an event entirely or only captured its fading remnants. Webb's sensitivity allowed scientists to observe thermal and chemical changes in real time, to chart the dispersal of debris clouds, and to model the energy propagation through Neptune's dense atmosphere. This collision also rekindled a sense of cosmic vulnerability. For all the technological and scientific advances humanity has achieved, this sudden violence unfolding on a distant planet reminds us that space remains an unpredictable, dynamic frontier. The same processes that shape the early solar system, chaotic collisions, gravitational perturbations, and violent transformations, are still at work today. Earth's relative stability may be more of a fragile gift than a guaranteed constant, a realization that adds urgency to ongoing efforts to understand and perhaps one day prevent catastrophic impacts closer to home. There is a broader philosophical dimension to consider as well. Events like this impact are stark reminders that planets, stars, and entire systems are not permanent fixtures, but actors in an ever-changing cosmic play. Over vast time scales, planets can be shattered, atmospheres stripped away, orbits changed beyond recognition. Neptune's collision demonstrates that even the mightiest planetary bodies are subject to the whims of fate, mere moments away from dramatic transformation by forces larger and older than humanity itself. The scientific world now finds itself at the precipice of a new era of discovery, driven by the capabilities of the James Webb Space Telescope and spurred by the questions raised by this collision. There will be countless follow-up observations, theoretical papers, and heated debates as researchers scramble to understand exactly what happened, how often it happens, and what it means for the broader narrative of the solar system. Questions about the origin of the impactor, its composition, and its journey through the solar system will fuel years of inquiry, potentially unlocking secrets about the birth and ongoing life cycle of the planetary family to which Earth belongs. In the weeks following the detection, simulations were run using supercomputers to reconstruct the collision. These simulations suggested that the object likely fragmented upon impact, sending high-velocity shards deep into Neptune's interior, perhaps even altering the planet's internal structure in minor but measurable ways. If true, then every layer of Neptune's atmospheric and magnetic personality may now bear the fingerprints of this violent encounter, encoding the story of the impact in ways that future generations of astronomers will continue to unravel. On the observational front, the debris cloud thrown up by the impact presented an opportunity to study the physical properties of Neptune's atmosphere under extreme conditions. The expanding shock wave from the collision revealed complex patterns of atmospheric movement, helping to refine existing models of how gases behave under the planet's frigid and high-pressure conditions. This knowledge is not only valuable for understanding Neptune itself, but also for interpreting data from distant exoplanets that may share similar compositions and climates. One of the most tantalizing possibilities raised by the event is that such impacts could play a role in the mysterious phenomenon of Neptune's heat. For decades, scientists have puzzled over why Neptune emits significantly more heat than it receives from the Sun. Perhaps periodic infusions of energy from massive impacts contribute to maintaining its internal heat budget. If so, it means that what was once thought to be a slow, static cooling process is instead punctuated by sudden injections of violent energy, reshaping not just the outer layers, but the planet's very thermal heartbeat. For planetary scientists, the impact was a rare, perhaps once-in-a-lifetime chance to observe the complex chain reaction triggered by a cosmic collision in a real-world environment. The lessons learned will ripple outward into many fields, from understanding planetary system formation, to refining models of atmospheric chemistry, to preparing for the remote possibility of defending Earth from future impacts. The collision on Neptune becomes a microcosm for understanding how chaos, destruction, and creation are intricately intertwined in the universe's grand design. The James Webb Space Telescope has already revolutionized the way humanity sees the cosmos, but by capturing this event, it has demonstrated a power even more profound: the ability to witness the solar system's raw, unpredictable vitality in real time. As the data continues to pour in, each new finding adds another brushstroke to the vivid, chaotic painting that is Neptune's story. A painting made not in calm, predictable lines, but in the furious, incandescent strokes of cosmic violence. This singular event underscores a fundamental truth about the universe: that it is not a finished sculpture, but a living, breathing thing, constantly reshaping itself through the dance of gravity, collision, and evolution. Neptune's recent collision, unveiled by Webb's unfailing gaze, is not an isolated event, but part of an ongoing saga stretching back to the solar system's fiery origins and stretching forward into an unknown future. The stars may seem still from a distance, the planets serene, but up close, the universe tells a story written in the language of fire and motion, of chance and inevitability, of creation through destruction. And in that story, Neptune's recent wound will forever be a chapter, a fleeting yet monumental testament to the restless heart of the cosmos. In this scenario, the collision on Neptune, revealed by the James Webb Space Telescope, is more than a snapshot of cosmic violence. It is an invitation to rethink the nature of planetary environments in regions of the solar system long considered dormant. As more detailed images and readings flooded in, scientists realized that the repercussions of such a colossal impact might extend even to Neptune's complex system of moons and rings. Early data suggested that the energy from the collision could have perturbed the orbits of some of Neptune's inner moons, a phenomenon that had never before been observed in real time. Tiny moons like Naiad and Thalassa, which orbit perilously close to Neptune, may have felt slight shifts in their delicate gravitational dances. Even slight changes in their velocity or orbital radius could create cascading effects over centuries, subtly altering the architecture of Neptune's entire satellite system. Some models even predicted that the collision's gravitational reverberations might gradually destabilize smaller moonlets, causing them either to crash into Neptune or to be ejected into space as rogue objects. If confirmed, this would show that a single impact event can fundamentally alter the long-term evolution of a planet's moons, a revelation that could transform the way scientists interpret the histories of other moon systems, from Jupiter's Galilean moons to the varied companions of Saturn. Another aspect revealed by the Webb data is the impact on Neptune's faint and ghostly ring system. Neptune's rings are dark, narrow, and composed of clumpy dust and ice particles, vastly different from the bright, broad rings of Saturn. Following the collision, several ring arcs displayed unusual disturbances, as if ripples had been transmitted through the particles themselves. These disturbances might allow scientists to measure the properties of the ring material with unprecedented precision, providing rare clues about the mass, density, and even the possible age of Neptune's rings. This discovery suggests that ring systems around planets might be more fragile and transient than previously thought, subject to dramatic reshaping by sudden external forces. Deeper analysis of Neptune's atmospheric changes uncovered another striking phenomenon: the appearance of newly formed chemical compounds that had not been previously detected in significant quantities. Among these were complex hydrocarbons, likely formed by the extreme heat and pressure generated by the impact shock wave. Such molecules can act as the building blocks for organic chemistry, hinting at intriguing parallels with early Earth's own volatile, chemically rich atmosphere. Although Neptune itself is far too cold and inhospitable to foster life as we know it, the creation of complex molecules in the wake of an impact shows that collisions can serve as cosmic laboratories, initiating chemistry that under different circumstances might lead toward biological processes. Furthermore, the energy released by the impact temporarily ignited enormous auroral activity at Neptune's poles. These auroras, driven by the interactions between Neptune's magnetic field and charged particles released by the collision, were unlike any seen before. Observations indicated that the auroras were far more intense and widespread than typical solar wind-induced phenomena. This temporary supercharging of the magnetosphere offered a unique window into how planetary magnetic fields respond to external shocks, information that could be invaluable when interpreting auroral signatures on exoplanets observed around distant stars. The temperature anomalies recorded in the immediate aftermath provided some of the most exciting opportunities for planetary scientists. Infrared sensors detected a sharp and temporary warming of localized regions on Neptune, spreading from the impact site in complex asymmetrical patterns. These patterns revealed previously invisible currents in the atmosphere, high-speed winds, vortex formations, and deep convection cells that scientists had theorized but never directly observed. By tracking how heat dispersed through the atmosphere, researchers were able to refine models of heat transfer on gas giants, bridging gaps in understanding that have persisted since the first Voyager flybys decades ago. Meanwhile, theorists are proposing that the object which struck Neptune may have originated far beyond the Kuiper belt. The very idea that an object could journey from the frozen periphery of the solar system and slam into a gas giant underscores the interconnectedness and volatility of even the most remote regions of space. In attempting to model the object's trajectory, scientists were forced to revisit assumptions about the gravitational influences that shape solar system dynamics. Small perturbations from passing stars, unseen dwarf planets, or even ancient remnants from the solar system's formation could subtly nudge distant objects onto new paths. The Neptune impact becomes a case study for the enormous domino effect that a tiny gravitational shift can produce across astronomical distances, ending in a collision with a planet visible across the gulf of space. Another extraordinary insight from the Webb telescope's observations concerned the visual afterglow of the collision. The light emitted and reflected by the impact debris was unlike anything previously cataloged. Analysis of its spectral fingerprints suggested the presence of exotic forms of ice and rock, some potentially unknown on Earth. These exotic materials, likely preserved in deep freeze since the earliest epochs of the solar system, could hold invaluable information about conditions during the era when the Sun and planets first formed, offering a rare opportunity to study matter from the solar system's infancy without needing a space probe to physically retrieve samples. The impact also stimulated renewed discussion about Neptune's internal structure. Traditionally modeled as having a small rocky core surrounded by a thick mantle of water, ammonia, and methane ices, Neptune's true internal composition remains largely a mystery. The way the planet absorbed and redistributed the shock energy from the collision is providing new constraints on the density and layering of its internal materials. If the shock waves propagated more quickly or more slowly than expected, it could reshape our understanding of Neptune's interior. In parallel, the dramatic event has reinvigorated arguments for more dedicated missions to the ice giants. Unlike Mars and Jupiter, Neptune and Uranus have been visited only briefly, leaving much about them unknown. The collision serves as a vivid reminder that these planets are dynamic, evolving worlds, not mere frozen relics. Some scientists argue that a Neptune orbiter, equipped with seismographic tools capable of sensing internal oscillations induced by impacts, could unlock secrets not only about Neptune, but also about the formation of planets around other stars. Astronomers are also closely watching for potential secondary phenomena resulting from the collision. One hypothesis is that the disturbance in Neptune's gravitational field could influence the trajectories of nearby objects in subtle but measurable ways, perhaps causing a small rain of comets toward the inner solar system. If so, Neptune's collision might inadvertently lead to a temporary uptick in comet sightings from Earth in the coming decades, providing another spectacular reminder of how interconnected cosmic events can be across unimaginable distances. In the broader scheme, Neptune's collision forces a reassessment of risk across the solar system. If massive impacts can still occur around the gas giants, it stands to reason that the inner planets, including Earth, are not entirely shielded. The rarity of such events on human timescales belies the reality that, in cosmic terms, catastrophic impacts are inevitable. The Neptune event is a clarion call for renewed investment in planetary defense initiatives, including better tracking of near-Earth objects and improved deflection technologies. The collision even has ramifications for the search for habitable exoplanets. If massive impacts are common throughout the galaxy, they may periodically sterilize planetary surfaces, reset biospheres, or alter atmospheric compositions dramatically enough to be detectable from light years away. Understanding the frequency and consequences of such impacts in our own system helps to frame the probabilities and histories of distant worlds, many of which are observed only as faint, flickering points of light. From an observational perspective, the event demonstrated that modern telescopes like Webb are not just tools for passive exploration, but active participants in real-time discovery. Future missions might be equipped with instruments designed specifically to catch transient, dynamic events like planetary impacts, atmospheric explosions, or even the early stages of planetary formation in distant star systems. A more dynamic view of the cosmos is emerging, one that recognizes not just the grandeur of ancient stars, but the ongoing, volatile dance of planetary evolution. The story of Neptune's collision is ultimately a narrative of forces both ancient and immediate. It is a reminder that the planets we think of as timeless and eternal are actually shaped and reshaped by random, high-energy events that leave permanent marks. Neptune, serene from a distance, now bears a scar that may endure for millennia. A scar written in swirling clouds, disturbed magnetic fields, and altered orbits. The beauty of the universe lies not in its stillness, but in its ceaseless transformation. The James Webb Space Telescope's observation of this collision is a rare and privileged glimpse into the vast, ongoing story of that transformation. It stirs a primal awe, a reminder that even at the farthest, coldest reaches of the solar system, where sunlight is little more than a memory, creation and destruction continue their endless, intertwined dance. As scientists continue to pore over the flood of data, new questions arise faster than old ones are answered. What was the chemical composition of the impactor? Did it carry with it isotopic signatures that could reveal new insights about the outer solar system? How exactly did Neptune's magnetosphere absorb the blow, and what faint echoes of the impact might still be reverberating unseen within its fluid depths? Each answer will birth a dozen new inquiries, each more thrilling than the last. Neptune's collision will not remain an isolated chapter in astronomy textbooks. It will inspire new generations of astronomers, planetary scientists, and dreamers who will look toward the distant, twinkling blue dot and remember the moment when the universe revealed its capacity for sudden, majestic violence. They will build better telescopes, launch new missions, write new theories, all sparked by the fire of curiosity lit by this singular, stunning event. The cosmos, vast and indifferent, has once again chosen to speak in a language of power and mystery. Thanks to the James Webb Space Telescope, humanity was there to listen, and in doing so, we find ourselves more connected than ever to the grand, tumultuous universe we call home. In this scenario, the collision detected on Neptune by the James Webb Space Telescope has proven to be not merely a singular event, but a doorway into new fields of study that will likely dominate planetary science for decades. As observations continued, one surprising revelation emerged. The impactor's materials left a lingering veil in Neptune's upper atmosphere, a subtle haze unlike any previously observed. Rather than dissipating quickly as initially expected, this haze persisted, forming new stratified layers within Neptune's atmosphere. The stratification suggests that foreign material from the collision integrated itself into Neptune's atmospheric chemistry, initiating new reactions and potentially altering the planet's weather patterns for years to come. This new atmospheric layer has a complex interplay with sunlight. Although Neptune receives a faint amount of solar radiation compared to the inner planets, the introduction of foreign particulate changed how the atmosphere absorbed and scattered the incoming light. Initial analysis showed a shift in the planet's albedo, particularly in the infrared spectrum. This adjustment, though seemingly minor, has vast implications. It affects the planet's overall energy balance and could potentially influence Neptune's climate cycles. For a planet once thought to be relatively climatically stable on human timescales, such a disruption illustrates how vulnerable even gas giants are to sudden external forces. The observations revealed something else equally profound: the presence of shock-heated water vapor in the high atmosphere. Neptune's atmosphere normally hides its water content deep beneath thick layers of methane and hydrogen. However, the immense heat generated by the impact forced water vapor upward, breaching layers that had remained untouched for millions of years. For planetary scientists, this unexpected revelation provides a rare, real-time glimpse into the deeper atmospheric reservoirs, offering fresh data that could redefine models of planetary formation and structure not only for Neptune, but for all ice giants. Extending the scientific focus beyond Neptune itself, researchers began to investigate how such a cataclysmic event might influence nearby interplanetary space. The impact injected a cloud of microscopic dust particles into the surrounding environment, creating a temporary exosphere, a tenuous ring of material orbiting along Neptune's gravitational field. Similar phenomena have been hypothesized for exoplanets subjected to heavy bombardment, but this observation provides the first direct evidence of a planetary body generating an artificial exosphere due to a single collision. Tracking how this dust disperses offers insight into how ring systems might form around other planets, and even how planets might accumulate or lose mass over astronomical timescales. The collision also prompted astrophysicists to revisit their models of orbital resonance across the solar system. Neptune plays a crucial role in maintaining the structure of the Kuiper Belt, its gravity shepherding countless icy bodies into stable resonances. The sudden addition of mass and energy to Neptune, even if relatively small, could cause minute changes in its orbit or rotation rate. These tiny changes, compounded over millions of years, might ripple outward to destabilize orbits in the Kuiper Belt. This concept, known as gravitational cascading, means that a single impact on a gas giant can set off chain reactions affecting regions of space billions of kilometers away. A profound realization that challenges earlier assumptions about solar system stability. While scientists race to understand the planetary science of the event, astronomers studying distant systems have begun applying the lessons from Neptune's collision to exoplanetary research. For instance,